Alright, so maybe there has never been a calculus lecture dedicated to a song or a song dedicated to a calculus lecture before, but there's always a first. This lecture, that song is dedicated to the definition of limits. Let me start from the top here. Last time we introduced some new ideas. We find it much easier to handle these limits first. We define them, we practice them, we learn the famous 4 techniques. That's these. And then once we were done with the outsides, we went inside and defined it, and we saw that sometimes things don't match, and the things get a little strange, and so there was this necessity to define right limits and left limits and two-sided limits. And it was nice that while we were, we had already developed all the methods, that all these methods that work at the endpoints also work inside of the two-sided limits. That's where we stopped last time, but today we want to make it right. The problem with these things is that a lot of them are just guesses at the end of the day, and so we now have ideas to make them much better than guesses. We have ideas to make them stand on very firm ground. And the idea is precisely the idea that we're doing today, the definition of a limit. But to make it right, we're going to need a lot of your brain cells. So we're going to need your full attention here. Put your game face on. If your spouse is talking to you, you got to tell them, hey, it's serious time. If you're on chatting with your friends, texting, whatever, Twitter, that's it. If you want, this is going to require a lot of attention. So if you want to get it, we got to focus completely. Here's the definition. There's actually 2 of them. Again, we do the ones at the end point first, and then we do the ones in the middle, because that seems to be the best way to introduce it. I think pedagogically, that you learn it a lot better. Once you've got the handle on the sides, you can do the middle stuff. Here's the definition. We only say that the limit of f of x as x goes towards infinity is equal to L if, and only if the following is true. If for every real number epsilon greater than 0, there exists a real number m such that whenever x is larger than m, it guarantees that the distance between f and L is less than epsilon. Got it? Exactly what you would expect, right? No, you wouldn't expect that. It took people thousands of years to do it. That's the definition. And the first time I took calculus, I didn't get it. I wish I would have taken a little time to treat it better and tell it how much I appreciate it. When I first took it, maybe I didn't love it that much. Okay. So that's the problem. When people first take calculus, many of us don't get it, and it takes several times to just get the hang of it. But there's another problem. What if you only take calculus once in your life? Well, which as most people do, most people don't become math professors or math teachers, and so it's a shame, because this is really a jewel of thought. So I want to try to do my very best to make it right. Just in case this is the only time you take calculus, I want to make sure I do the best job that I can at explaining this definition, because it has far-reaching consequences, and because it's nice to see. One of the jewels of thought of modern times, of all times actually, were the 9 symphonies. Again, 2 definitions. One going towards infinity says that for every real number epsilon greater than 0, there exists an m such that blah 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 blah. And then the other definition, the one with x goes to a constant c, has a very similar flavor. For every real number epsilon greater than 0, there exists a real number delta greater than 0 such that when x is delta close to c but not equal to c, then that guarantees that f is epsilon close to L. I told you this is not easy. That's why people don't get it the first time. They don't love it the first time. They don't tell it how much it means. They don't treat it nice. So that's the setup. For the next couple hours, we want to take time to appreciate it, this jewel of thought. And that's all we want to do today. Just understand that definition, and which means exactly that, and understand this definition, which means exactly that. If we can do that, we will call it a successful day. And so I've been thinking a lot about this, about a good analogy to make this more accessible. So I thought about golf here. You know, in golf, everybody knows the name of the game here. You just have some sort of putting green. You have to hit the ball, and sometimes it goes curvy and whatever. And the idea is to try to get it into the hole, and that's when you call success. And you could trace the. Suppose you leave a mark here, a documentation of the path that the ball took. We can ask questions like you would in limits. But in order to motivate why we would even ask the question, suppose something happens. So the ball is going here, and boom, when it was about to get there, something magical happened. The world had some sort of discontinuity, some mishap, something. It's as if maybe Harry Potter came and flying with his little wand here and zapped the earth, and boom, everything disappeared. You don't even know if it went in the hole or not. At that point, who knows? Who knows if it went into the hole or not? Just something totally weird happened. The ball disappeared. The world stopped. And that's the problem. That's what happens when you plug things like infinity into a number. You get outside. You get outside of the world that we can compute, so to speak. And so that's exactly what happens when you get indeterminate forms. That's exactly what happens with limits. And then we have to resolve the following question: did the ball get in a hole or not, or you know, what happened? Suppose you were trying to prove that it did. You would ask, you know, how could we prove? I want proof that the ball went into the hole. But right at that instant, the world stopped, and we can't figure it out if it went or not. And so, you know what we do? We don't figure out if it went in the hole. That's not a question we address. It's not a famous question. Rather, we try to prove it was going towards the hole. That's the best we can do. Or said differently, it got very, very, very close to the hole. If we can do that, we'll be happy, and that's called the limit. It's the best prediction. It's not actually what happened at that instant, but it's what it appeared to be happening. For that, so we're not going to prove that it went into the hole. We don't do that. We're going to prove that it got very, very close to the hole. But suppose you wanted to practice proving that the ball got really, really close to the hole. This may be hard to do. In fact, it is hard to do, to prove that it got close to the hole. An easier strategy might be just to prove that it got a little bit close. Not that close, but just a little bit close. If you can practice proving that it got at least somewhat close, then there's hope that maybe you can prove that it got really, really close. You follow? So let's start off with something sort of very modest. Let's ask if you can prove that the ball got within 1 foot of the hole. Simple question. Did the ball get within 1 foot of the hole? Here's a trajectory. Did it get within 1 foot of the hole? To document this, we can actually make little marks here on the time. Say when it was first putted, the time was equal to 0. Maybe this was 1 second. Maybe here the time was 2 seconds. Maybe by the time I got here, it was like time was equal to 10 seconds or whatever. We can document the path relative to time. And we're documenting it so we can answer this question: did the ball get within 1 foot of the hole? And the layman person would say, yeah, it got at one point it got within 1 foot of the hole. That's what a layman person would say. Just any old reasonable person would say that. But then a mathematician would say, no. I want proof exactly at what time. What time can you prove to me? I need the exact time. What time was it within 1 foot of the hole? If you don't tell me the time, I don't believe you. Did it get to within 1 foot? Yes or no? It's not enough to tell me yes. I need to know the time. What time? And because we documented it really carefully, maybe you can figure out that the time was something like, I don't know, I'll just make something up, 15.3 seconds. So, okay, you got the time. I believe you now. It probably got within 1 foot of the hole. If you can prove that to me, I'm happy. And what does that do? Does that prove that it got really, really close to the hole? No. It just proves that it got kind of close. It got within 1 foot. That's what it proves. You say, yes, I proved it, but do you prove that it got within 1 foot? And then you don't know what happened. For all we know, maybe after it got within 1 foot, maybe there was a slope over here on the putt and it went out that way, or maybe it went out that way. You don't know. Maybe it never really got really, really, really close to the hole. All we know is that we got within 1 foot, or maybe it stopped after that. So this is good practice for proving that it got close, but it's not the final thing. You can say something like this, and people did say something like this. Whoa. I'm slowing down on purpose. You can say something like this. Okay, I believe you. You told me the time. I believe that the ball got within 1 foot of the hole. But I challenge you. Challenge you, does the ball ever get within a half a foot of the hole? I don't believe you. Does it? In order to prove it, I don't want just a simple yes. I want time. I want proof. When? Exactly when did it get within half a foot of the hole? And so you go on and you go back to the documentation of the events that happened, and you make another circle half foot from the hole. This is all the distance that's within the hole. This is everything that's within 0.5 feet of the hole. You document the path. You observe the time, and you say, whoa, at t was 23.85 seconds. Winner, chicken dinner. I'm within the range. I'm in the zone. And so you could go back and conclusively say, yes, it got within a half foot of the hole, and I could prove to you exactly when it got there at exactly 23.85 seconds from the putting of the ball. And then you say, okay, I believe you now. I believe that it got within half a foot. But you know what? At the end of the day, that doesn't prove anything. Maybe after half a foot it fell off. Can you prove to me that it got within 1,000th of the hole? And there we go again, making a 1,000th diameter or radius circle around this hole and checking for the time. When did that happen? Maybe it happened at 35.2 seconds. And then if you can document exactly, then I'm starting to believe you. Okay, it got that close. But then you still don't know if it fell off after that. You see how skeptical you have to be to think like a mathematician. You have to be super skeptical. We want proof, mathematical proofs, not wishy-washy stuff. This is one of the beautiful things about mathematics, is that you can actually prove things, and that makes them stand on much firmer ground than not proving them. In fact, we don't want to do it for 0.001, because then we would ask the next obvious one, can you do it for does it ever get 0.000001? And we would go on forever. That's not pretty. And there's no permanent place in mathematics for ugly stuff. So instead of keep doing it for every single possible radius, we did it for 1 foot, half a foot, 1,000th of a foot. Instead of doing it for every possible radius, what we want to do is we want to get a little template, a block, and you do it within blah, with radius blah, and then do all the work and all the computation, all the documentation. Say, yes, if the radius is blah, I can do it. And that does all of them at once, all the possible radiuses. So it could be as big or small. You could do everything with just one template. We could call this R. We can rephrase the question. Okay, it gets within 1,000th of the foot, but does it ever get within R units of the hole? Within the radius R. And then, now we're getting somewhere. Because now, all of a sudden, check it out. The following sentence should make sense all of a sudden. Unbelievable. Look at this. Alright, so once we get past that, then we're in a good spot, because now all of a sudden this sentence starts to make sense, and you start to treat it much nicer, and you start to tell it how much it really means to you, because suddenly, look at it, you're saying for every real radius r, the radius could be small or big, it doesn't matter, for every single radius in the world, and no matter how big or small it is, there exists a time. I could tell you exactly the time when, after that time, the distance from the ball to the hole, this is distance, is less than that radius r, so you're inside. That right there should make a lot more sense than the original definition, but the power in the analogy is the fact that the analogy and the actual definition are so similar, they're nearly identical. So if this makes sense, you're in a super great spot now, because this will make perfect sense. They're almost identical. Look at that. For every real radius r greater than 0, there exists a real time m. That's exactly the same. For every real number epsilon greater than 0, there exists a real number m, such that after that time, if x is larger than that time, then the distance from the function to the limit is less than epsilon, such that well, the one of them has time and the other one has x's, but the other one has a distance from the hole to the ball is less than r, and the other one has a distance from the function to the limit is less than epsilon. They are nearly identical, and that makes the analogy really, really powerful and effective. The only thing that's left to do now is actually doing a couple problems with functions. We've already done one with the golf. We want to do a couple examples with functions, and remember, this is the definition for limits going towards infinity. And then once we do a couple examples using functions, we want to try one that's not where the limits are going towards infinity, but limit in the middle, and explore that definition as well. But once you get a hold of this one, the other one's much easier. So we got our work cut out for us. Let's try an actual example. So we take a familiar function, one that we already know what the limit is. If you try the plug-in method here, by the plug-in method, the limit as x goes towards infinity would be 3 minus 1 over infinity, which would be 3 minus 0, which would be 3. The limit is 3. By the way, all the 4 techniques that we studied before, they're still true. In fact, the definition is not really helpful to find limits per se. It's not a finder, it's more of a checker. It helps you prove that whatever you think the limit is actually a limit. It's a checker, not a finder. Anyways, the proposed limit on this one is, of course, 3. So made an asymptote here at y equals 3, and you see the ball. If you can imagine the putting of the ball here, it gets putted and it goes that way, that way, that way. And we're arguing that it's going to get infinitely close to 3. So we're arguing that pretty soon it'll be within a certain range, and we can make this as small as we want it. But of course the ball is moving, so we can't do that forever. So what we do is we put the range over here, and maybe we just make a little line here and say this is the range. If it's within this range, it's within whatever this distance is. This will be your epsilon. So let's actually do it. Talk is cheap. Of course, to do it, we want to do the same thing that we did before. We want to practice before we actually do epsilon. Let's practice with something easier. Oh yeah, let's review the question too and see how the analogy goes. How do we prove that the function gets to 3 as x goes towards infinity? The answer is we don't. We don't prove that it gets to 3 as x goes to infinity per se. The limit idea is a little bit different. The limit idea would say instead of doing that, we want to prove that the function gets really close to 3 as x goes towards infinity. What happens, it's actually at the point, or like infinity, the limits, we may be concerned, but the limits question is not concerned with actual points. It's concerned with the patterns of what happens as you're going towards there. So let's practice. We'll start off with a very modest question. Does the function ever get within 0.2 of 3? First, let's try to understand that. What's 3? Within 0.2, that would mean 3 at 0.2 and down 0.2. That would mean 3.2 and 2.8. That's what it means within 0.2 of 3. From 2.8 to 3.2. And the question is, does it ever get there? Of course, it does. Look at the function is going. It's going up. And the question is, does it ever get here? This is 2.8. Here, that is 3.2. Does it ever get in this range? And of course it does, and you can even pinpoint it. This is exactly when that happens. That's when it gets to that range. That marks the spot. And so we make the little radius here, 0.2. We label it. This is 2.8. And this is 3.2. And then to figure out, this is a really important point, to figure out exactly where it crosses, I'm going to think about it the following way. The following way I think would be helpful. To figure out exactly what that point, this is going to be my m, so that all the x's that come after that are guaranteed to be in this range. They're guaranteed because the function will never go above 3 because it's 3 minus some positive thing. And I'm using the assumption that the graph is correct and it's going up, up, up. It'll never come down. There's no slopes over here where it would fall. So basically, to figure out when it's in this range and it stays in that range, all I got to do is figure out exactly this point. And after that point, I'm guaranteed to be within 0.2 of 3. Now, slow it down. Now to find that point, the best practice is to figure out which lines intersect there and set them equal. And let's decipher that. This is one of the lines that intersects that point, that defines that point. That line is 3 minus 1 over x. Y is equal to that. I got it from here. And then the other line that intersects there is this line right here. This line right here, and that line right there is defined by y is equal to 2.8. That's it. This line and that line, that's their equation. So if I set them equal to each other, what do you think will happen if I set them equal to each other? Well, I can solve this. I'm not afraid. Negative 1 over x is equal to 2.8 minus 3, so negative 1 over x is equal to negative 0.2. So 1 over x is equal to 0.2, so 1 over 0.2 is equal to x, so x is equal to 5. What did we just do? Well, we found out exactly that this x is equal to 5. This is my m. If this point is 5 right here, then and the graph is accurate, then anything after that puts me within 0.2 of 3. And so I'm ready to answer the question, does the function get within 0.2 of 3? Yes. Not just am I ready to answer it, I'm ready to prove it. Yes, it does get within 0.2 of 3, and I got proof. As soon as x crosses the line x equals 5, boom, I'm in the range. I'm within 0.2 of 3. And now you're beginning to appreciate it and to love it. And you're beginning to be happy that this definition is going to be yours within the next 30 minutes. Of course, that wasn't enough, man. That just proves that it gets within 0.2 of 3. 0.2. Any old chump can do that. We really want to know, does it get really, really, really close to 3? For example, does it get within 0.0001 of 3? 1,000? Oh no. Does it? Well, we have to make this little range smaller. and the line probably has to go further and further and further till it crosses. Let's keep it white for consistency. We want to know exactly as the ball's going there, when does it cross that line? When does it guaranteed? I need to find proof. Right here, this is my proof. For all x's beyond this, boom, I'm in the range. That's what I want. In this case, assuming that it's positive the way or going up the way we've drawn it, all I gotta do is figure out when this line, the white line, which is y is equal to 3 minus 1 over x, all I gotta do is figure out when that one intersects my other one. What is that one? Well, if it's within that of 3, this is 3, and this would be 2.999, and this would be 3.001. By the way, if the graph was coming up from above, you would probably use it, it would be a different equation. You'd set it equal to that one right there. All you gotta do is put your fingers on which two intersect. That one intersects and that one intersects. The equation for this one was 3 minus 1 over x. The equation for this one is 2.9999. So whenever these two are equal, winner, winner, chicken dinner. So I set them equal to each other. That would give me 1 over x is equal to 2.999 minus 3, so negative 1 over x is equal to negative 0.001, so 1 over x is equal to 0.001, so x is equal to 1 divided by 0.001, so it's 1000, winner, winner, chicken dinner. I could tell you exactly when this will happen. I can prove to you. If you're asking me, hey, as the graph goes, how do I know it gets really, really close to 3? Does it ever get within 1000? Yes, it does. And I got proof. The minute x crosses this line, m equals 1000, the minute x becomes larger than that, you're in the zone. And that's a nice thing to do. See, this is the way the proof works. You give me how close do you want it, I get you there, and then if we can keep doing that all day, then it gets really, really, really close. How close? As close as you want it. Because if we can do this all day, you give me an epsilon, I give you the m. You give me another epsilon, I give you the m. Then we can play this all day long, and I will win. And I will always be able to prove that yes, it gets very, very close to 3. That's the genius of the definition. Well, no, that's only a little piece of it. There's more. Wait, there's more, but we can't do it all in one day. Today we just want to understand it, okay? Take it easy. Take it easy, my friends. Take a little time to do things here and there. Maybe I didn't know you. Yeah, so we did it for 0.2, for 1000. We want to do it for a generic blah. See, if you do it for a generic blah, it's like doing it for a template. Then you'd have a template where you could always prove it directly and say, hey, you want to be within blah? Yeah, I can get you there. Whatever epsilon it is, you give me the epsilon. I'll keep it yellow just to be consistent. I don't care what epsilon you give me, I can always come back to you with a m, and that will guarantee if x is larger than m, I'm within epsilon of your 3, no matter what epsilon you give me. If we can figure this pattern out with a template, then we're in good shape. And the other one was just practice so that we could actually do it. This line right here would be, check it out, we're going to do exactly the same now. With having practice, this would be painless. This is y is equal to 3, and I got to come down epsilon, because that's this little distance right here. That distance is epsilon. See? This little radius is epsilon. So, and by the way, this one would be 3 plus epsilon is equal to y. Both of them are equal to y. This one, of course, is still the same. It's 3 minus 1 over x. I put my fingers right here where it's crossing. Which two lines are crossing? That one and that one. That would be this one and this one. These two are crossing. So to find out that point, which is exactly what that's my winner, winner, chicken dinner point. Winner, winner, chicken dinner right here. As long as I cross that, I'm in the zone. To find out that point, I set these two equal to each other. just like that. Oh, this is duck soup. Let me solve. So I got 1 over x is equal to negative epsilon. I subtract the 3 from both sides. Then I kill the negatives. Then I solve for x. I need to know my x. Yep, I need to know my x. So 1 over x is equal to epsilon. So 1 over epsilon is equal to x. That's it. Winner, winner, chicken dinner. So this m right here is 1 over epsilon. So this is like a little machine. Look. For point 2, boom, I got my x. If x is larger than 5, I can prove it to you that it gets within point 2. You want to try me again? You don't think I can get you closer to that? You think it never gets within 1,000? Boom, I get you. I tell you, I prove to you exactly when it's within 1,000. You want more? You want more? Give me any epsilon you want, and immediately I'll give you the m that guarantees that when x crosses that m, you're in the zone. What does that prove? That proves that you could get epsilon close to 3 for any possible epsilon. That gets you really, really, really close to 3, as close as you want it. And that's the depth and the genius on the definition. Okay, let's take a moment to savor that before we do the next example.
Little things.
So with this one we've done before. We've said that if you've got a number that's smaller than 1, like this one in absolute value, and you raise it to a high power, intuitively you think 98% times 98% times 98%, that thing's going down real quickly and eventually we'll get to 0. We've said that. Now it's time to make it right. Now it's time to make it tight. We can actually prove it with epsilons and m's and the rigor of 2,000 years of the smartest people walking around. The rigor of the jewel of thought that is the definition of limits. We can do it now. We've got it all right here. Everything that we need. Let's make a little graph here. So here's your function. This time it's going down, 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 down. And the question is, does it get close to 0? Because that's what we're proposing. We're saying, hey, this is going towards 0. Just to say it is not enough, we want to prove it. So, should we just go for the epsilon, or should we get a little practice, a little appetizer here with an actual number? Instead of doing epsilon, maybe we can move the epsilon aside and say, hey, can we get us within 0.001? That should be like practice, so that when we do the real thing, we'll have a better idea. Want to try that? Can we get this within 0.001? Well, then look at the picture here. This, if that's it, then 0 plus 0.001, that makes this graph right here, the graph of y equals 0.001, and that makes this graph, the graph of y equals 0.001 negative. And you put your fingers, this is where your fingers come in. If you want to know that point right there, which I do, I want to know exactly this point right here, because assuming that the graph is accurate, the function's coming down, 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 and at one point it crosses exactly the line I want it to cross, and it gets in the range that I want it to get. And that's the whole point that proves my case. It proves that exactly at that time, when x's are larger than that, or my x's are larger than that, I'm in the zone. So that's why I really, really want to know this point, because that's the proof. If you want to know that point, and that point is defined by the intersection of two graphs, what you got to do is figure out which two graphs are there. That's one of them, and the other one is this one. Y is equal to 0.98 to the x, and what you want to do is you want to set them equal to each other, because those are the two that intersect here. And that's so we do that. We set them. We solve it. All right. Let's see. How do we solve that? I'm not afraid. So I would slap an ln on both sides. Let's go with yellow. ln on the left side, 0.98 x is equal to ln of 0.001. Bring down the x, so I got x times ln of 0.98, and that's equal to ln of 0.001. Divide both sides by this. Get ln of 0.001 divided by ln of 0.98. And you compute that on the calculator. Let me see if I got it. I think I had it here somewhere. Haha. So I computed this ln of 0.0001 divided by that. It's equal to 341.9. 341.9. So x is approximately that. What does that tell you? It tells you if you went back to the picture at exactly this point, 341.9, roughly that point, as soon as x crossed that line, boom, you're in the zone. And so we can answer the question conclusively. Does the function get within 0.001 of L? And I say yes. Not only do I say yes, I prove it. If x is larger than 341.9, I'm just going to round off to 342 just to make sure. Hey, if 341 works, 342 is even better. 342. If 342 works, 343 is even better. So it's just going down. And that's nice. But, of course, that only proves that it gets within 1,000th of the limit. We want more. We want to know that it gets within epsilon of the limit, no matter what epsilon is, any real number. So that's, if you can get this would be like a little template, and it would be easy to prove all the other ones after that, because all you do is plug it into the template. Let me see. For that, we would have to solve something like this. 0.98 raised to the x is equal to epsilon, because you're instead of being 0.001, you take this away, and now we bring mark our epsilon. So then this y would be no longer that, but then that y would be y is equal to epsilon, right? And so let me think. That's looking good. You find the point. This is the point we want. You find out which two functions. Well, in this case, will you forget about that? Whoa. The annihilator. So these are the two equations that we have to set equal to each other. The 0.98 to the x and the epsilon. Those are the two that intersect here. And so we go to work here. That's why I set them equal to each other. Then we'll do a little log on these. Slap a log on both sides. 0.98 x is equal to log of 3. Bring it down. X ln of 0.98 is equal to ln of epsilon. Divide that, so I get x equals ln of epsilon divided by ln of 0.98. Oh, we're doing good now. Look at that. Look what we just did. Ln of 0.98 divided by ln of epsilon. I got a little machine here, a little template, a little generator. You give me the epsilon, and in half a second I'll tell you exactly when I'm in that range. You want to be within 1 millionth? No problem. I plug in 1 million there for epsilon. You want to be within 1 billionth of the limit? I got your back. I'll plug in 1 billionth right here for epsilon. And immediately I can I can prove to you exactly at what time you'll be in that range. And what does that prove? Well, that proves that you get really, really close to L within any epsilon whatsoever. That's the depth and the power of the definition, the analogy. Alright, that takes care of the limits going towards infinity. Now we should take a moment and then see how that fits together with the limits going from both sides, okay? Maybe take a little break, pause it. You took a little break, intermission. Now we're ready for the second definition. That's the one in the middle, the two-sided one, where C is somewhere in between. We will only say that such a limit exists if and only if, for every epsilon greater than 0, there exists a delta greater than 0 such that x being delta close to c but not equal to it guarantees that f is epsilon close to L. It should sound almost identical to the previous one with just a couple little differences. Let's see what that means in a picture. Suppose you take a function like 3x plus 2. And you want to find the limit at 5, a two-sided limit. We already know what the limit is. 3 times 15, the limit's going to be 17. That's based on the plug-in method. Now we want to make that tight. We want to actually prove that our suspicion that it's 17 is actually correct. So the picture would go something like this. As your x's move closer and closer and closer to 5 from both sides, closer and closer to 5, we want to know the function. You know, you're walking over here, you're walking over here on the y's are going this way and the y's are going this way. We want to know, does it ever get within a certain amount of the limit 17? If you look at 17 here, this is 17. It's the funkiest 17 I've ever seen. This right here is 17. This is y is equal to 17. And what I want to know is, does it ever get within, say, 0.5 of 17? Let's practice with that. So you'd say, okay, within, let's practice, does it ever get within 0.5 of 17? What does that mean? 17 plus 0.25, that would put you here. And then 16.5, that would put you here. And we're asking, will it ever get in this range? In that range and that range. I want to know, when does it get in that range? Well, surely as your x's are moving closer and closer and closer, you're over here getting closer and closer from both sides. Your x's are over here getting closer and closer. At one point or another, it does get it in there. But now I got to do it from both sides. And the question is when. I need proof. How close do I have to be to 5 to be this close to 17? And so we draw these lines to help us, guide us. This is the point we want to. As soon as you cross that point, as your x's are coming this way, as soon as you cross that point, you're in the range. Or from the other side, as soon as you cross that point, boom, you're in the range. You're in the zone. You are within 0.5 of 17. And now that all we have to do is just algebra. For example, let's do this one on the right. To find out that point, I need to know exactly what point is this, x equals what, and then this x equals what. At which point that I cross here, at which point am I guaranteed to be in the range? To figure out this point, you figure out which lines intersect here. This line intersects, this line is y equals 17.5, and this line intersects y equals 3x plus 2. So I would go on and solve that. I would say, okay, I want 17.5 to be equal to 3x plus 2. Look at that. This line and that one, when these two intersect, that'll give me an x value. That'll give me this x value, the one that tells me exactly at which point, the one that proves to me at what point am I in the range. So I would go on and solve this. Is 15.5 is equal to 3x, therefore x is equal to 15.5 divided by 3, whatever that is. You guys can use a calculator if you want. Let's see if we can use a calculator. Let's see if we can turn the light on. See if we can you guys see that? A little bit. 15.5 divided by 3, what is that equal to? 5. X is equal to 5.166 with the little bars. Let's just run off to 1.67. That tells me this point right here is 5.167. And then I got to figure out that one. To figure out that one, you got to think which lines intersect here. This line intersects here. So this is one of them, and this line intersects right here. This one is y is equal to 16.5, and that one is equal to that. So one way to do it would be to solve this equation. You would solve 16.5 is equal to 3x plus 2, therefore 14.5 is equal to 3x, therefore x is 14.5 divided by 3, therefore x is approximately, and you just go something like this, 14.5, and then 14.5 divided by 3, that gives you f 4.8333, 3, many threes. That gives you this one right here, 4.833. Now the distance from here to here is 0.167. The distance from here to here is 0.167. So this is telling me exactly the distance. How close? See, now I've got two radiuses going on here. I got a blue radius here. How close do I have to be to 5 to guarantee that I'm in the 0.7 neighborhood of 17? For every neighborhood over here, for every little radius, I need to find a radius down here. That tells me, that proves to me how being that close to the 5 guarantees being that close to the 17. And we've done it here. We've done it. The closeness that you have to be is 0.167. Now the fancy way to write that is we say that if the distance from x to 5, this distance is less than 0.167. Actually, I rounded up, so I'm going to round down. I'll just go 0.16. If the distance, that makes it even smaller, which is better because now I'm for sure in there. If 0.16 works, anything smaller than that would also work, 0.15, because it would make it even smaller. But the logic, the reasoning goes like this: if x is the distance from x to 5 is 0.16, then you're in here in this little radius, then you're guaranteed that f minus L, the function minus limit, will be less than 0.5. And we've succeeded. We've shown, that was just a little practice to show, for example, this sort of reasoning. We start asking, does the function ever get within 0.5 of the limit? Yes, and we have proof. But now we don't do it this way. Now we say if x minus 5 is less than 0.5 or 0.16, then I can prove to you if x is in this range, my y will be 0.5 of L. Okay, and that was just practice. What we want to do is for general epsilon, and that involves a little bit more algebra. And it's probably instructive to go back to this one the way we did it and do it again in a different way. In a different way that will help us do this one. So let's do this one again. Here's what we want. Ready?